Ja, god dag, Nødtrommel. Velkommen til dette så hattjørlødene, hadde vi kunne si. Her vi Helma Mariu Tróndheim for å Verja sine Ph.D. Richard. Og dette her verer en chance her vi for at bruke enskamålet, så at framløver og spårninger og alt det verer enskån. So let me just start to welcome Helma Mariu Tróndheim today to give her the opportunity to defend her Ph.D. thesis. And also I'd like to welcome our examiners. We have 3 examiners as usual. Boje Jensen is chairing the committee. And Boje Jensen, he is the director of digitalization and technology at Ørsted in bioenergy in Denmark. He is also an affiliated professor at the University of the Faroe Islands. And Professor Jensen holds a Ph.D. in electrical engineering from Newcastle University in UK and has published 85 peer-reviewed papers, mainly within energy engineering. And we have also 2 examiners from abroad, and they are Göran Andersson, Professor Emeritus at the Swiss Federal Institute of Technology, ETH, Zurich. And he is actually he has been the head of the Power System Laboratory from 2000 to 2016. And his interests are in power system modeling, control, analysis, and dynamics. And he is a fellow of IEEE, which most of you might know the meaning of. And he is among his distinctions, the 2016 IEEE PES Kunter Power System Dynamics and Control Award can be mentioned. And then we have Thomas Ackermann. He is the founder and the CEO of the renewable power system consulting company Energy Nautics. He has over 25 years of worldwide academic and consulting experience in the area of power systems and power system operation, with focus on grid integration of renewables generation as well as electrical vehicles. And he is actively involved in lecturing at universities and within capacity building of renewable energies into existing power system around the world. So very welcome to all of you. I think I will just mention that Helma Maria is actually one of the first bachelor students we had in energy at the University of the Faroe Islands. It was a course called Engineering in Energy and Environment. So it's good to see that she has started with us, and he has gone through a master, and now she has done a Ph.D. Work at the university together with SIV and together with the University of Aalborg. The way we are doing this is that Helma Maria will present her work, and then Göran Andersson will have some questions to her, and after that we will have a break. And the break will be around 15-20 minutes. And during the break you are able to ask me to be allowed to ask questions to Helma Maria. And there will be a possibility for having one question per person at most, but it should be within these 20 minutes. And the questions should, of course, be related to Helma's work specifically. Please give me a note if you would like to have some questions. Give me a note before the end of the break. So if there are any questions, then there will be a session with that maximum to 30 minutes. And after that, we will continue with the second examiner, Thomas Ackermann. And after that, we will, I think, not move too far away from here, because then the examiners are going to another room to evaluate the presentation and the work of Helma Maria and decide if she has passed the exam. This is an exam for Helma Maria, and in the end of the day, she hopefully will pass the exam. So after they have been in another room for making this evaluation, they will come back and tell us if Helma Maria has passed the exam, and the chair of the examiners board will tell us. But now, before Helma Maria gets the floor, we will have the chairman to announce why the examiners think that the work of Helma Maria is eligible for a PhD defense. So please, you have the floor, Boje Bech-Jensen.
Thank you very much. We, the assessment committee, have evaluated the thesis that Helma Maria has submitted. We found that the research questions have been clearly formulated and discussed. The state of the art has been presented with a comprehensive literature review, which means that she has explained the context and relevance of her research. She's presented her methodology clearly and applied it to solve a number of engineering and societal problems. Her research demonstrates societal impact by recommending how the Faroe Islands could achieve a fully renewable electricity supply. And as Dr. Ackermann pointed out earlier in his presentation this morning, this work is not only relevant for the Faroe Islands, not only for island communities, but continental countries as well, where the grid is run as an island grid. Her engineering impact is clearly demonstrated through a combination of simulation and measurements, where her simulation results are validated with a full-scale system, and this is rare for a Ph.D. The thesis is concluded with a summary of the work and proposed further work. Based on all of the above, the assessment committee unanimously agrees that Helma Maria Trondheim is ready to defend her thesis orally. The examination will be conducted by my colleagues, Professor Göran Andersson and Dr. Thomas Ackermann, and as chair of the assessment committee, my role is limited to a more formal part to ensure that we stick to and adhere to the rules and regulations of both the University of Aalborg as well as the University of the Faroe Islands. Thank you.
Okay, thank you. Then we'll give the floor to Helma Maria to present her work. The title of the thesis is Ensuring Supply Reliability and Grid Supply and Stability. I take it once more. Ensuring supply reliability and grid stability in a 100% renewable and electrical sector in the Faroe Islands. So please, Helma Maria, the floor is yours.
Thank you. Yes, thank you for the introduction as well. I will first introduce you to the agenda of my defense. I will start with an introduction to the research project. We'll focus on the background of it, and I will introduce the Faroese power system, and then I will present the project objectives set in this research project. My research has been divided into two different topics, and I will start with the topic which is called expansion planning towards 2030. And here I will present the methodology that I developed to obtain a tangible roadmap towards 2030. And I'll also present some additional optimization results, and finally the 2030 roadmap that I have proposed. Then I had the second research topic, which I called power system simulation, and it revolves around parametrizing and validating a power system model of the Faroese power system. And I also analyzed the frequency and voltage fluctuations in today's grid. And I also conducted some power system stability studies towards 2030, focusing on the island of Føroyum. Then I will present my conclusions and future work. So if we start with the introduction. As many of you may know, in 2014, SEV announced the 100 by 2030 vision. And this was also later adopted by the government. But in order to reach this goal, we need to investigate how can we reach this. And this is the main motivation and background behind my research. As all of you probably know, the main motivation behind renewable energy is the environmental advantages, because we can limit the CO2 emissions from the power production if we install more wind turbines and solar panels and such. This being said, there are also some challenges with transitioning towards a more renewable energy sector. And if we consider the fact of balancing the energy production, we have the difficulties that the resources are not 100% predictable, even though they are, the forecasts are increasingly accurate. But we also have a natural intermittence in the resources, so we can have a longer period of time where we don't have any rain or wind and solar and such. And this is not something we can change. In addition to this, we also have the changing seasons, so we have different resources during the summer than in the winter, and therefore we also need to store the energy throughout the year. In addition to this, there are also some challenges with renewable energy and power system stability, because from renewable energy we get the fluctuating production, or can at least, with the varying wind speeds and clouds covering the sun. And then we also have the fact that renewable technology is typically different from the traditional synchronous generators, because we have an inverter-based interface, which means that we don't have the same inertia and short-circuit capabilities, and therefore we need different methods to deliver these. In addition to this, regulating capacities are also more limited, because we cannot increase the wind speed or the solar irradiation. So we can always down-regulate, but regulating up is a difficult task when you have renewable resources. Finally, we also have this Faroese power system, which is electrically isolated from other power systems. And this makes it more prone to this production than other systems are. If we take a look at the Faroese power system here on your right, we can see a map where all the power plants and ancillary services and substations and cables and lines are mapped. And in the Faroe Island, it is the power company SEO, which is in charge of both transmission and distribution, and currently also has a de facto monopoly on production. But this is about to change. We have 7 isolated grids, and my research has focused on the main grid and Suðuroy. The main grid connects 11 out of 18 islands. In addition to this, we have 5 really small grids with their own isolated system. We have voltage levels ranging from 400 volts to 60 kilovolts, and in 2021 the generation was 424 gigawatt hours, and with 38% renewables, so there's still a way to go. I listed the demand as well, where in the main grid we have 42 megawatts, and in Suðuroy 4 megawatts. The total generation capacity in the Faroe Island is 168 megawatts. And the storage capacity, and this is hydro reservoirs, is 12.3 gigawatt hours, roughly. So if we take a look at the project objectives, I have 2 main objectives. And the first one is, what is the best suited roadmap in a 100% renewable electricity sector in the Faroe Islands, based on resources and economics? The second one is, how can we obtain a stable electricity supply in a 100% renewable electricity sector? And I'll go further into details of these 2 objectives as I present the 2 different research topics. So if we take a look at the first objective, here again have the first objective listed, and the method to assess the first objective was to conduct a state-of-the-art of expansion planning tools and case studies. We also needed to assess the available energy resources and the potential production they could have in the Faroe Islands. I also assessed the feasibility of the production and long-term storage technologies, and this is linked to the previous where we assessed the available energy resources. And then I conducted different analysis of the optimal energy mixture between the production and storage, and investigated how different technologies and different costs can impact the overall system. We developed a procedure to obtain a tangible roadmap from an economic optimization, and finally I've obtained a roadmap for the Faroese power system based on the economically optimal energy mixture. So if we take a look at expansion planning and the state of the art of that, so we can say that there are similar systems with similar visions. And for example, a good comparison is the islanded system in Madeira. But we still need our own solution to, it's not like we can copy their solution to ours, but we can get some information and learn from each other. Expansion planning studies, they are typically conducted as economic optimization. However, this leads to some disadvantages because then the size of a wind farm or a cable can increase year by year. And this is not something that's done typically. Either you install a wind farm or you don't, and instead of increasing the size each year. And I discovered that it is necessary to have practical considerations to be included in this method to obtain a hands-on roadmap. And we also need the roadmap in order to reach the goal and to be able to conduct future power system simulation of the system as well. So this is a flow chart of the method that I've developed, which is we have utilized the tool Balmorel, which is an optimization tool. And then I've added this step here, which is a roadmap generation, where it translates the optimal results to a tangible roadmap. And then I validated the roadmap, and the solution of that is the roadmap that I will present. If we take a look at the inputs, in order to conduct an economic optimization, we need to have some inputs. And for example, it is the policy constraints, and I've used a linear reduction in the CO2 emissions towards 2030, because the expansion plan has to assume that there is 100% renewables in 2030. In terms of the system model, we need to specify the existing and committed capacities. And the demand projection also has to be conducted, and in this case it also considers heating and transport being electrified. The cost used based on the existing system is based on known operation and maintenance costs, and fuel cost projections are taken from the Danish Energy Agency. Finally, you have to define all the different investment options, where I've defined based on local resources and suitable locations. And I've set maximum capacity on each location to ensure that we are not ending up with a result that optimizes more turbines in the locations than there is space for. And the costs of the future investment has been based on previous projects and some technical catalogs as well. So if we take a look at the optimization part, Balmorel optimizes the dispatch in the system and investments simultaneously. But the dispatch is optimized per hour for each plant and each transmission connection, while the investments are optimized annually for each location and technology type and such. I have in the optimization considered different scenarios in order to investigate the impact that these have on the system. And I conduct a sensitivity analysis varying the costs of technologies and fuel costs. So if we take a look at some of the optimization results, I have compared here 4 different scenarios, where we have the main scenario, which considers solar, wind, pumped hydro, and then we have the second scenario, which also considers tidal energy, and then the third considers the option of burning biofuels or carbon neutral fuels at the Sund power plant. And the final is without a restriction on CO2 emissions. So we can see what is economically optimal and what is controlled by this limit on CO2 emissions. And up until 2024, I simulated from 2020, but up to 2024, the results are nearly identical. And these are the generation capacities. But when we go to 2026, we can see some differences, but they're not big. But as we get closer to 2030, the differences between the scenarios increase quite significantly. And for example, we can see that solar is only included in the main scenario where we don't have tidal, we don't have biofuels, and we have a limit on the CO2 emissions. Tidal energy can lower the generation capacity quite significantly, and so can biofuels if these are options. I've added some noteworthy optimization results here. And these are that renewables, according to the simulations that I have conducted, are the economically favorable option, up to 86 to 87%. After that, we pay more than we receive for the renewable generation. And especially when we go from, my simulation resulted in 96% in 2028 and 100% in 2030. And this step, these 4 last percentages, they double the need of storage, which is in pumped hydro in this case. I have also, found out that the results are not that sensitive to the investment costs and fuel costs, but because these scenarios with tidal and biofuels have a larger impact on the total configuration than the sensitivity analysis does. But it should be mentioned that in fuel costs, I've used plus minus 20%, and I think we have had maybe larger increase in fuel costs since then. But at least with plus minus 20%, there was no significant difference. Then I'll state that tidal energy can have a major impact on the future power system, as it can reduce the generation and storage capacity by 18% for generation and 75% for storage. And the reason behind the reduction in storage is because we can get the baseload production from tidal energy if we place them in different locations. So if we take a look at the next step, this is the roadmap generation step. And this has been based on the main scenario because the goal is 100% renewables. We don't know where we have tidal energy in a few years, and and the same of the costs of carbon neutral fuels and such. So the roadmap has been based on the main scenario. In order to translate the optimized investments, I've defined that the investments should be in realistic project sizes. And this is to increase the realizability of actually using the expansion plan instead of being a purely theoretical study. Also included the fact that the learning curve of the operators has to be considered because each investment in this power system has a quite significant impact on the operation of the system. Also consider practicality as with regards to how things are structured, for example, with wind farm tenders and such. We have an example of a wind farm here, and this is in Sandøy, where you can see the problem that I mentioned, that the wind farm size is increasing year by year. But as I mentioned previously, we will not install a wind turbine and then another one and do that like that. Therefore, we need to have a more tangible approach to it. And here I've divided this wind farm into 2 steps of 18 megawatts because it was considered too large to install 36 megawatts at one location at this stage in the system. This is the roadmap that is the result of the optimization and the transition of the optimization. And the things with red borders are committed capacities, and some of them have been moved since then. But I will just show you where the wind farms are located. So you can see that this roadmap is actually very specific in terms of locations and such. And the same with the cable connections. And the pump storage system is, of course, located in the same place. But then we have a need for a battery system in Føroyum to balance the system, the energy in the system. Then finally, we have a need for solar in Føroy, Sandoy, and up north. In order to validate the model, or the roadmap, I used the roadmap as committed capacity into Balmoral, and then I simulated it again. And the criteria to validate the model was that the production should be 100% renewable in 2030, and that the economics of the system should be similar to the main optimized scenario. And here you can see the comparison of the economics of the main scenario and the roadmap, and you can see that there are variations, but the variations are not that big, and in total I think it was 4%, the roadmap is 4% more expensive over this time, a 10-year period, than the main scenario. And of course, when we change and optimize results, we will end up with a more expensive solution. Yes. Then I'll move on to the next objective, which I've given the short title Power System Simulations, which is quite broad, but I will explain to you more specific what I've done. So the sub-objectives to meet the second objectives are to conduct a state-of-the-art of power system model regulation and modeling, and then to model the power system in Dixon's Power Factory, which is software. And it has to be based on both today's configuration and the future configuration, according to the roadmap from the first objective. I also had to develop and apply some validation guidelines for the dynamic power system model. And in order to validate this model, it's also necessary to conduct some tests on the system to obtain model data for the model validation. The voltage and frequency variations in today's system have also been analyzed. Then the grid has been simulated and analyzed with the proposed expansion plan and the test scenarios based on common and known grid disturbances. And in case there were some stability issues, the need for expansions in this have been addressed. I also looked into whether or not we can use an approximate model of the main grid when we're analyzing the stability on Føroy, instead of including a full detailed model of the main grid, because this increases the computational time quite significantly, even though it's a small system. And finally, to provide lessons learned from Føroy to the main grid, because while the first objective focused on the main grid and Føroy, the second objective focuses mainly on Føroy, although some of the simulations presented in the thesis are conducted on the main grid as well. So if we take a closer look into power system regulation and modeling, you see that there is a need to provide a ancillary services using alternative ways, and there have been different control strategies and technologies developed to do this, and can be found in literature and some of them also in real life. But having an accurate power system model is crucial in the renewable transition, because we need to know whether or not the system can handle the expansions conducted in the system. This being said, obtaining a validated model can be difficult because there are so many different parameters and controllers, and each impacts each other, at least many of them do, and this increases the complexity of the system. And I tried to use methods found in literature, but after trying a few of them, decided to, we identified some problems and then combined different methods in order to obtain a model of the validated model of the Faroe Islands. This method utilizes both system-wide simulations, hybrid simulations, and multiple scenarios. And I will go into more details on that in the next slides. We also validated the models, the static model through a load flow, where we checked the measurements in the system of our operation scenario, and made sure that the current flow and such is representing the reality. The wind turbine models have been validated in cooperation with the manufacturer. So we implemented the models and then discussed the simulation results with the manufacturer, which approved of the results. Then finally, also developed a model of a secondary frequency control, which is manual in the Faroe Islands, but this was needed in one of the simulation studies. So if we take a closer look into the model parametrization and validation that are conducted, and focus first on the first part here, which is to ensure that we have enough data available for the validation. Because we need to have some measurements of grid disturbances in order to be able to capture the dynamic response of the generators. So if no data is available, you need to conduct tests, and you also need to prepare the data for the validation. Then you have the middle part here, which can be quite challenging when you have to choose a regulator model. But there are some guidelines for AVRs which can use, and the models for especially diesel governors are very limited, so it's not a lot to choose from. But after this, you have a model, you need to parameterize it. And I've done this first using a hybrid simulation parametrization. And a hybrid simulation means that I've used only a subnetwork, and then I set the voltage source, defining the measured frequency and voltage, and then we see the behavior of the generator based on that. And if that is the same as the measurement, the active and reactive power, then we have been able to parameterize the model. And then, after parameterization, we evaluate whether or not this is good enough, and if it's not, you need to maybe adjust the boundaries of parameter, or maybe use a different regulator. But when we only look at an isolated part of the system, we don't really get the whole story. So we need to conduct a system-wide simulation where we take the whole system and initiate the same disturbance in the grid, and then we see how the whole system reacts to this. And if this can be validated, then we have obtained a good set of parameters. But if not, we need to conduct a second parametrization, and this is using a system-wide simulation. But since a system-wide parameterizing with a system-wide simulation would require a lot of computational time and such, we focus only on the governor or AVR that is not performing as it should. So this is an example of the need for a system-wide simulation parameterization at Verja in the main grid, where after this step, where we did the system-wide simulation validation, we saw that the parameters found did not result in a result close to the measured values. But after conducting a second parameterization focusing only on these two AVRs, we improved it quite significantly, and there's still room for further improvement. This is an example of one of the generators in Føroyum, where we used hybrid simulation parameterization on an AVR, and we used 5 different events simultaneously. And 4 of them have quite similar results to the measurement, but the top one here is deviated. There's a steady state error. But it was after several trials, the response was not getting better for that scenario, while the other ones were fine. So try to move on to system-wide simulation for this event. So here we have all the generators that were online during this event, and here we have the same generator, and you can see that the behavior is actually quite good compared to the original results through hybrid simulation. As I mentioned, the secondary frequency control in the Faroe Islands is manual, and that means made an effort to model human behavior. But this can only be done in the way I've done it with historic data. So basically, I've added a signal here, which has been measured when the person regulating has pressed up or down, and then I've translated this into a signal based on the droop and the power settings of the generator, and then I used it as an input to the governor to control the output. And I have an example here for a hydro turbine in Føroyum, where the blue is measured and red is simulation without this controller. And you can see that without the controller, it's quite constant throughout this period. But when I added the controller, it goes down. It's still not perfect, but you can see that the correlations factor between measured and simulated have increased from 0.58 to 0.9. So that's quite good. These lines, vertical lines here, are when the regulator is pressed up or down. Blue for up, and green for up, and red for down. Then I analyzed the frequency and voltage fluctuations in the system in a paper that I published, and where I compared today's system with both. This was focused on Føroyum, where we included both the wind farm and the PV panel in Sumba. But for the second case, we excluded the PV panels, and case 3, we excluded the wind power, and for case 4, we excluded both. And you can see the frequency fluctuation and the time here, or the duration. And what you can see that for case 1 and 2, which include wind power, the fluctuations are quite high, but for the second cases without wind power, they're significantly lower. For the voltage, there's not a big difference, but it should be mentioned that this voltage is measured quite far from the actual wind farm, and since voltage is more of a local problem than frequency, this could be an impact on that, but I have not looked further into that. This just shows some of the parameters related to the graph, and you can see that the fluctuations above 100 millihertz have, for case 1 and 2, are above 30% of the time, while for case 3 and 4 it's below 1%. And we also see a reduction in the voltage, but it's not as significant. Then I've conducted the simulation towards 2030 in Føroyum, and this figure here shows the expansions in Føroyum from the roadmap. And I've expanded the model with these expansions. And then I'll include one of the simulation results here, where I've simulated load rejection for 2020, 23, 26, and 2030. And you can see that in 23 there are some oscillations in the frequency and voltage. And in order to avoid that, try to increase the synchronous condenser, and that solved the issue. But this is not like a final investment ready to say yes, we need to install a synchronous or a larger synchronous condenser. But this is at least one way of solving this issue. And we also say that from 2026 we can see quite different behavior, and this is because we have here a cable connection to Føroyum, and since the main grid is quite way larger than the grid on Føroyum, the main grid supports the grid on Føroyum during falls. And therefore, we also have a lower rock-off as well. Yes, I also simulated when I included the cable, I tried to simulate the main grid with a detailed model, approximation 1, which was based on infinite inertia and the short circuit power of the system, and approximation 2, which is the where I calculate the inertia from the detailed model and then used it in the approximation. And what we can see that neither of the approximations show accurate results compared to the detailed model. Approximation 1 shows a constant frequency, and this is due to the infinite inertia. But the voltage is quite similar if you compare it to the detailed model. And for approximation 2, the frequency is significantly better, but then we have a challenge in the voltage, which does not show the same behavior. And the reason behind this is that this approximation cannot fully capture the batteries in the main grid and how they support the grid on Føroyum during the simulation. So if we go from Føroyum to the main grid, we can say that fluctuation, of course, will be an issue both on the main grid and in Føroyum, but these can be minimized in the main grid because we have the option of geographically distributing the wind farms. The events tested on Føroyum are relatively large compared to the grid of Føroyum, but not compared to the main grid. And therefore, we also need to have some additional scenarios to investigate, which are severe events in the main grid, before we can conclude any specific on that. If we reduce the Føroyum while investigating the main grid, we would see the same thing, that the battery on Føroyum would not be captured by the approximation, but I don't know how relevant it is to investigate Føroyum with an approximation when it's the smaller grid compared to the main grid. Because the benefit of doing it with approximating the main grid when analyzing the Føroyum is that you reduce the computational time. We also need to investigate several years, not just start and end, because some of the implications are seen in between. So we need to conduct continuous simulations and to be able to see what's going on. So if we move on to the conclusions, first have research topic 1 here, and you can say that there are some disadvantages with when the aim is to obtain a tangible roadmap due to the if you only use a priori optimization. And we have assessed the potential production from generation and storage technologies and the feasibility of that. The optimal energy mixture has been found based on the criteria set, and the impact that different technologies, for example, tidal energy, and the costs have been identified. A method to develop a roadmap has been defined, and a 2030 roadmap has been obtained as well. For the second topic, system simulations, you can say that there are several different methods, but applying some of these, of course, I've not applied every single method that there is out there, but some of them that I applied did not lead to sufficient results, and therefore we moved on to developing a method. A model of Føroya has been developed and parameterized and validated, and the dynamic simulations conducted in this study have highlighted some of the challenges associated with the transition towards 2030. Modeling the main grid with the approximate model leads to inaccurate results, but of course it depends on your needs, what you need the simulations for, and the system. But in the case where I compared the detailed model with the approximated models, we show some difficulties. Some of the lessons learned in Føroya can be transferred to the main grid with regards to the system stability. The concluding remarks are that the main contributions that this research project is providing is the method to develop a realistic and tangible roadmap, and also the results that have shown that tidal energy can change the whole system or the future power composition. And then we also have this method to validate and parameterize the dynamic models. And I've identified some issues with network representation of the main grid, or reduction. And the results found here are interesting and beneficial for other power systems, and especially similar isolated systems. For the future works, I would say that things are changing all the time, so the roadmap has to be updated on a regular basis. You also need to address different stability scenarios, because the ones conducted in this study are only limited to Føroya, and they're only being conducted for different disturbances. And you can also say that I've used a lot of time on validating and parameterizing Føroya, but this should be improved on the main grid as well. So thank you for your attention.
Thank you very much. Then we will give the floor to, or the word to Göran Andersson, please.
Okay. Thank you. First of all, I would like to congratulate you to a very interesting piece of work that you have briefly presented here. I mean, it's a lot more into what you have done during these years that we can see on this impressive book that you have given us here today. I found it very interesting to read your thesis. I learned a lot, and I was thrilled of the challenges you have and how you managed to solve them. Perhaps not completely, but at least you're on a good way to manage these things. Now, just want to state that my role here is to be critical, so I don't take it personally if I put questions, because that is part of the game in a PhD exam, that you should be challenged. And so I have a number of questions here, and I hope that you're willing to answer them and discuss them with me. And I will start from the beginning and then go through, and some of the questions I think you can answer quite easily, and some others might require some more discussions and input from you. So, I start on page number 2, where you have a statement about that wind speeds and direction can change suddenly. Here on the Faroe Islands, that was a surprise to me. I thought there was a steady wind from the west all the time. And you put your windmills up on the top of a mountain, and they were not gusts. I mean, if it's down in a valley, in another type of geography or topography, this could be valid. But is this valid at the Faroe Islands?
Yes, it is. The mountains, they create a lot of turbulence, and that creates some challenging wind conditions. And also seen that for when the wind farm on Føroyum was being installed, you started with one wind mast, but then the manufacturer said that this is not good enough. You need to, because we see that there's a lot of turbulence, so we need to measure the wind at another location, really close by, if you consider the distance in reality. But this just shows that there are some challenges with the wind speeds in the Faroe Islands.
Okay, thank you. Well, I put down this question before coming here. This is my first visit to the island, and we made some touring the other days, and then I saw the topography here, and that's quite different. In the same sentence, you have statement about clouds and PV, that they can have very sudden changes, the PV in feed. But is that true if you have a lot of PVs? And here you have only one, as I understand it, today, and there it could be true. But if you go to other countries like southern Germany, for instance, then you will have an averaging effect from clouds.
Yeah. Of course, if you distribute the PV panels, which also is the goal when we will increase the integration of solar, you can limit this. But especially when there is a little bit of wind, the clouds move quite fast. But if you distribute the PV panels, then you limit that issue. But it's still something that I think could be an issue, and also, as shown, I think it was this morning by Dr. Ackermann in one of his slides, the variation from the PV panels on a cloudy day, they're quite large, but if you distribute them, then you limit that, and that's also the same for the wind speed, if you distribute the wind farms, because you have local phenomena, and
you have kind of a temporal accuracy and a spatial accuracy, and you cannot achieve both simultaneously, I think. Then a lot of what you have discussed here is about stability issues in the second part of your thesis. And then in the beginning on page 3, you quote a definition of power system stability that I'm partly responsible for, because I was in this working group that proposed this definition in 2004, I think it was. So it's quite a long time ago, and a lot of things have happened since then. My question is, do you think it's a good definition still, now with more fluctuating energy sources in the grid, and you have inverter interfaced energy sources and so on. Or when you have worked, has it been of any value to you, this, or would you like to modify this definition?
I would definitely say that it has been valuable because it's quite generic, that statement that I've copied there, because it's power system stability is the ability of a system to, I don't really remember, but after a disturbance to regain the...
Yeah.
And without going into further details and into what actually the problem is, but it's a disturbance, and that's the ability, the power system stability is the ability to regain stability after a disturbance. So I think that's quite still accurate, but I also know that there has been an updated or similar work group on this topic with defining more branches, because the original had frequency, voltage, and rotor angle stability. And now there are a few more. So I don't exactly remember the definition of those, but of course the power system is changing, and you cannot just say that this is what we have, this was defined, and now we stick to this. But so far in my work, I've not run into any challenges with that exact definition.
Okay, yeah, you answered my follow-up questions also. Actually, that it was in figure 1.2, if that you think that is valid, and you said that it should be extended.
Yeah.
And there was some work 2 or 3 years ago where they extended this to say the modern power systems. Fine. You have a statement at the bottom of page 5 and top of page 6 that I'm a little confused what you mean. And I read it to you, perhaps not all of it, that it's about disturbances in power systems. And you say that on isolated grids, like the Faroe Islands, these systems are much more prone to disturbances than a large interconnected system. I mean, disturbances for me is how many faults you have per kilometer of line. And is that higher here than it could be? But there are other systems too. Let me continue. Do you mean that the consequences of the disturbances could be bigger here than...
Yes, because of the lower inertia and the short circuit capabilities.
Yeah, because the disturbances per se is something that is not depending on the system, but exactly. Of course the consequences. Yeah. I believe that is what you mean. Yes. Then when you make your optimization here and then you come up with the roadmap, of course the assumptions are very important. Yeah. And one such assumption is the load curves you have. And if you look on your figure 1.5, that is on page 10, could one... sorry. Yeah.
What figure?
1.5, page 10.
Yes.
Where, and these, you say that these are average curves.
Yes.
Average load curves. So I mean, what usually you have a winter and a summer curve, and but you have looked on the average curve, and or this is aggregated over the year, or how should I understand this?
For the optimization, I've used a whole year measured per hour.
Yeah.
But what I'm presenting in this figure is where I've taken the average for each hour to obtain a typical day.
Mm-hmm.
But this is for each hour throughout the whole year in 2020.
Okay.
But in the optimizations, I've used the whole time series, so this has not been aggregated in the...
Mm-hmm. Okay.
Yeah.
But what is the difference between summer and winter here?
Basically, it's a bit higher in the winter.
Yeah,
but,
sure.
but the behavior...
But how much higher?
I'm not really sure.
Yeah, okay.
No, I don't have the numbers on that.
Okay, but you used then the whole year for in your optimization.
Yeah.
Fine.
So that should be accounted for in the optimization.
Yes. I'll come back to the optimization, and then I think what is really good here is your formulation of the research questions and the limitations you have, and because that kind of puts the limits of what you intend to do, and it's a disclaimer if someone tries to draw conclusion outside that area. It's not always you see that in thesis. Page 32. You have a statement about hydropower that it cannot be, let me see, I find it here. You say the environmental concerns that prohibits you from expanding hydropower in your system. So what are these environmental concerns?
In the past, received a lot of resistance to expanding hydropower because of the large reservoirs and when they're empty and how it affects the nature close by, and also because the hydro reservoirs use lakes from different locations. So there are tunnels in the mountains extracting the water from a lake maybe far away to the hydro reservoir, and then there's no water in that lake anymore, and therefore people and politicians have been quite resistant on expanding hydropower.
But couldn't you put limitations on that? How much you can, the filling levels and so
Yeah.
on? That is in
Yes.
all other countries with
Yeah,
hydro. There
that's-
are these limits and how fast you can empty and fill and so on.
Yes, of course, that is an option. But I think it's quite difficult to convince people that that hydropower is not that bad. It won't take all the water from your location. But of course, that's used in many countries, for example, Norway, where you have a limit on the flow. So you always have a flow in the,
Would it be expensive to
Yes, it is. It's expensive, but especially when you compare it to, for example, wind turbines. But you also have to consider the lifetime, because a hydropower plant has a much longer lifetime than a wind power plant. But yes, it is expensive to expand hydro in the Faroe
Okay. Yeah. But on the other hand, you have a very nice power source there if you have the hydro,
exactly.
as you show in your simulations later on.
Yes,
That
it would
your hydro
solve a
power
lot of
plant.
issues if we
Yeah.
could just use hydro.
Yeah, well, perhaps not only, but it could be a very important and substantial
Yes.
component in your
Agreed.
system. Moving on to the next page.
Yep.
33, tidal power is something that I was a little confused about this, that you, this 15%, and you, that you can maximally a maximum of 15% of the available power can be extracted before it affects the tidal stream significantly. And the reference is a report from EPRI, I think. I'm a little confused over that it's so low that 15% of this particular here. I mean, it's the whole Atlantic pressing on, and would it affect so much?
I will not call myself an expert on oceanography, but I think yes, it affects the tidal streams, but how much and what the effects are, I do not know that, but I found this limit in this report which said 15% and decided to go ahead for that because in the optimization I needed a limit because otherwise it will be just place tidal.
Yeah, of course there is a limit. It's not 100%, that is for sure. But
so I decided to use this 15%.
Okay, yeah. So then we come to say one of the core parts of your thesis, and that is this optimization, where you have used this Balmoral software doing it. And one question I have is why did you use that software? I mean, there are other softwares available for optimization
I looked into the different softwares and also have, I think I've cited one of a paper which compares the different softwares, and according to the needs that I had to optimize both investments and dispatch and be able to include, for example, tidal energy, chose Balmoral as the best suited, also because it's easy adaptable and open source code. And there's also that advantage that there was already a first edition model of the Faroese power system in Balmoral. I of course expanded that a lot and the different things, but I had somewhere to start from that. So that's basically why I chose to use Balmoral.
Do you know what kind of solver they are using in this? I mean, you formulate a problem and then you have an optimization solver. Do you know?
It's GAMS.
Yeah, GAMS is where you formulate the language, but you have a solver attached to it.
I don't know.
Cplex or a couple of them available, or perhaps you don't know.
No, I don't know.
No, okay.
Yeah.
Because that Cplex is one of the most powerful.
Yeah, Cplex sounds familiar, but I cannot say 100% sure that I...
Developed originally by IBM and used quite. If we should stick into the optimization, you choose this approach, and which means, as you correctly say here, that then defining a roadmap, you have to use the results and then kind of offline and by hand then pick out the exactly investments and so on.
Yeah.
I mean, there would be say, more direct approach with mixed integer programming, where you have integer variables where you say you install or not install, and also you have chunks of different sizes.
Yeah.
Was that something that you... Because then you would have gotten the results directly. I mean, it's much more challenging to optimize it, but...
Yeah. The thing is that I started the optimization with only Balmoral, but after we saw the results and how all the wind farms were just increasing and increasing, then I identified the need to do something about the results and not just observe them. And therefore I I've not used any other optimization algorithms. I tried once to export the results and then do a MATLAB code to then do some definitions, but I decided not to go ahead with that because, limited time and such. But that's also one of the future works that I've defined, that you could optimize the process of getting the tangible roadmap.
Many similar works you see when you have renewables, they use stochastic optimization. You have taken 1 year curve, but you could also have a stochastic distribution of wind and PV and so on. Was that an option that you were considering?
No, I have not considered that in this study. No.
Because now you kind of define this curve and it fulfills that.
Yeah.
But you don't know if you have a variation from that curve, what would the consequences be?
Yeah.
I mean, what is the probability that you will supply the load with the installment you have, that you could say that with 99% or whatever?
Yeah.
So that is also perhaps something you can do in the future.
Yes.
To look on these things. Also, I mean, you have here on page 40 you formulate mathematically the optimization problem, and if I should be a little critical, I think it would have been nice to have a little more explanation of of these equations. I mean, you can get it if you have the look on the your table 2.4, and then you can go back. But say a page discussion of what constraint 2.2 and so is, that would be very, very useful, I think. For instance, 2.4, that is your transmission constraint, I think, if I'm reading correctly.
Yes.
Yeah, and that is kind of static, so it's not, you don't have any dynamic line rating or something like that in winter time you can transmit more because it's colder and things like that. And also that is just, this question is probably just due to my ignorance, that you have no CO2 costs included, but you have this curve that it should be below that value, so it's kind of prescribed. Yeah. In that, so you are not part of this ETS system that in Europe and so on. Okay. You showed one slide. So you make this optimization, and as you said, you get results, but they are not directly that's not a roadmap. So you have to do that then offline, and you come up with these curves that you showed. I mean, when are you happy there? You showed these bars with different colors, and did you have a criterion when you are happy? And I couldn't find that directly in the text.
Yeah.
Yeah.
No.
I mean, it looks good, but I mean, you.
Yeah. No, there was no. From the start, there was no clear criterion because when I started or when I made this, I had no idea actually what to expect, how much it would influence. But I would say it is below 5%, and that, in my opinion, is considered to be close enough. And also discussed this with my supervisor at the time. we obtained these results, whether or not this was good enough. But either way, if it depends on who defines it, what is good enough, because this is not something that I've seen in literature, at least. So cannot just go and cite someone and say the roadmap should be more. But I also discussed it with the people at SEV, and who thought that this was within acceptable limits.
Yeah.
But there was no exact definition.
No. But you kind of felt when you were good enough. And
yeah.
That was. Yeah. Sometimes that is good enough to do it that way. Right. Okay. I think that my co-examiner here will also have some questions on these things. I must go back here, page 41. I have written something, and that I want to ask you about. Yes, you talk there, page 41, the first paragraph, a little below the middle. You say that, thus it is deemed necessary to account for the learning curve of the power system operators. So what do you mean, the learning curve of the power system operators, that they get more and more skilled, that they are bad at the beginning, or?
No, it's in order to obtain something that could actually be installed. It's thought that we cannot just say that everything's possible, and we can just install, I don't know how much at the same point of time. But yes, it's basically the skills of the operators to get used to the new system or to the new investments. For example, with dividing one of the wind farms into two pieces. Of course, you also have the option to just curtail. But what's the point of installing a lot of wind power if you're just going to curtail it because the system's not ready to handle it? Yeah.
So the operators, they have some instructions to follow in different situations. Do they have a, say, decision support tool, or how?
No, not really. But for example, with the inverter-based generation, today say that there's a limit that it will not go above 60% inverter-based, instantaneous inverter-based generation, and you have to stick within 49.5 and 50.5 hertz. But otherwise, it's actually quite individual on who the person is controlling the power production.
Thank you for your answer. Page 47. Here I have a question that is, I don't intend to be rude here, but not to you, but you say that you want to determine the losses in the system.
Yep.
Right at the bottom. That can be seen by comparing the production at the power plants and the consumption at the electricity meters. There is something in the literature called non-technical losses. Do you know what that is?
No, I'm not familiar with that term.
That is people stealing electricity. There are loads that do not put up a meter, and perhaps people are so honest here that something that you don't count on.
Yeah.
It's not a problem.
I don't know how big of a problem that is, but,
but
yeah, maybe not the whole difference is losses, but at least transmission losses.
I think my co-examiner has experience from developing countries where the so-called non-technical losses can be 10% or even more in India, for instance, that you've seen that people go up and hang on a wire. But I think that here in say, Scandinavia and Europe in general, that is not a problem. If it is, it's down on the, say, 0.000% or something like that. So, yeah. Okay. Let me see. Yeah, I had on page 62, that's a minor one, too, where you talk about the efficiency of pump hydro storage. You say it's 70%.
Yes.
Page 62.
Yep.
In the middle. The only difference between modeling a pump hydro storage system and a hydropower plant is that loading pumping capacity with a round-trip efficiency of 70% is added to the plant. But 70% is very low for a pump hydro storage, I would say.
Yes.
Yes. I mean, in Switzerland, I think you're counting on 85% or something like that.
Yeah.
I mean, it's more 90% when you turbine and 90% when you motor. So 0.9 squared is 0.81, and it's a little more than that, so 85%, and I think they are up to more than that, actually. This is very low, I would say. But it will probably not change the results very much, but it was a comment. Yeah, we discussed the, time is flying here, the roadmap there, and I think we are finished with that one. You had one statement on page 107 that, but I let's look on that one. That in conventional power systems, synchronous machines provide ancillary services required. I mean, it's a matter of definition. I think also in conventional systems today, batteries are used. In continental Europe, there are many where they use batteries for what you call secondary frequency control, and even for primary frequency control and for other issues. So it's there are other providers of it, and also, of course, flexibility. I mean, load response, that loads are responding to particular heat loads, which I heard you're doing here, but it's freezing houses that you use as flexible loads. And so it's not only synchronous machines, I think, in conventional systems. If we go to the next page, you have this plot of the primary, secondary, and tertiary control, which is correct. But the terminology has changed. I mean, now it's called the frequency containment reserve, the primary reserve, FCR, and frequency restoration reserve. And I think you mentioned it in the text, but your figure there is a little outdated. Yeah, it's the old terminology from NSOE you're using there. Then your chapter or chapters here on parameter or model determining the parameters of your models, I think is very interesting. And I looked in the literature list and your references, but I cannot find. There is some papers by Nelson Martins in Brazil, who has done quite a lot of work in this area. And you haven't read that. That is particularly for hydro plants in Brazil. Okay. And there's quite some nice work where he has made similar tests as you have done here, and then has a whole, say, toolbox and methods to get to the models. And I think that could be something to look into.
Yes.
And also in control theory, there is the whole area of system identification that is dealing with this issue. So that could also be worthwhile. Here I think that the constraint you have is you want to fit it into Power Factory.
Okay.
Is that true? That you use the models that you have in Power Factory?
Yeah.
How is it there? I'm not familiar with that in detail. Couldn't you define your own models?
Yes.
You can do that?
Yeah.
But you used standard models here?
Yes, because it didn't have any, on most of the generators, it don't have any information on the governors or the AVRs. So if it's my own model or if it's from the library of Dix Island, it's still not the actual model that, or we cannot be sure that it's the actual model that should be used.
No, but, well, I had answered the question in a different way than you did. Because I think it's going to be used by SEV later on.
Yes.
And that's a point to use these standard models there. On page 114, you define 3 different scenarios, or the test cases, I can
Yes.
say. Why these? Any?
Yeah. The first one, we wanted to see what does the system look like during steady state or semi-steady state without disturbances. It's still quite varying a lot, but we want to see what is the frequency behavior like and how does it vary throughout this week or over a whole week.
Mm.
And the aim was to be able to compare it to how will it look in the future. Then there is the load increase, and yeah, that was just to test one of how this will increase or how it will affect the power system, and don't think there was any really good explanation behind why it's exactly 5% load increase, but it's just to see the behavior of the system. And yeah, the third one was based on the fact that in the future this connection between Region 1 and Region 3 will be a very important connection, and therefore we want to see whether or not if we suddenly take this line out of service, what will the power flow be able to go the other way, or will it increase or result in a blackout, or what will happen if we get an outage of this important line?
Yeah, I agree. Number 1 and 3 are important, but the second one, you increase on all loads. I mean, an alternative would be to increase some loads, and
yeah,
that is natural what happens in the system, because then you have triggered other modes. Now it's kind of a you put everything up and down, and
yeah, it's maybe not realistic disturbance that all loads will increase simultaneously. That's I understand that.
And you do not excite perhaps interest modes. It depends on the system, of course, but then I found it was very you will see in the report, I think later on, that I like your way of writing here. It's easy to understand, and it's clear everything what you have done. And I found very, very few, say, misprints, let's call them. But there is one here, and that is you write on the last paragraph of page 115 that you have a 5% load increase shown in figure 5.7, but then in the caption it says that it's a load decrease, and it must be a load decrease because the frequency goes up.
Yeah.
So that was a small misprint there.
Yeah, that's true. Yeah.
Sorry, pointing it out. Let's take this first one here. Page 129. The load models here. That's an interesting topic, and there are several Ph.D. theses written on load modeling itself. But you had static models here in your simulations.
Yes.
Could that had an you say it has an insignificant impact on the overall frequency and voltage response in the investigated scenarios. But how many different load models have you checked? Here?
I just checked constant impedance, constant power, and the third one. When I say this is because when I was trying to validate the model, when I was doing it manually and had really difficult to get the accurate parameters, then we said, let's check the loads. Are they the factor that's impacting the frequency response? Because in some of the situations we could see that the response of the generators was accurate, but the frequency was not, and vice versa. And therefore I tried to change all the loads between the different types. And when I did this, there was little to no impact. But I've not adjusted the parameters and said how much percent should be dynamic and such. So it was just a very fast analysis of how these loads affected.
Because my many of the major loads here, they are of the fishing factories and the freezing, and that's compressors, induction motors, and they have a frequency response in them. So that's why I think that to have a dynamic load model, which is quite simple to implement, I believe, could be a better approach here.
Yes.
For the future. Okay. Then you do this optimization. You have the particle swarm optimization to when you decide the parameters, and you have this where you have the hybrid simulation and then the system-wide simulation you explained here. My question is, how you want to have the responses as close as possible. So you have some deviation, is if the mean squared, some mean squared, or what is it, or you do?
No, it was basically an engineering estimate. I discussed it with the engineers at SIV and with my supervisors as well. And because I did not find any definitions on or guidelines on this. How close should the rise time be or drop time and such. So I did not have a clear indication on how I should define this, if I should have a clear definition on the steady state or the drop or such. And therefore, it was basically an estimation of each scenario, going through it, and yeah.
But your PSO does an optimization. But what is the objective function? What is it optimizing?
Yeah, it runs through, I don't know how many iterations, and then it stops. And
but you must define when it should stop. I mean,
but there's a maximum iteration number. And in Perfect, you can also, you also have a definition on the objective function. But basically, when I run this, it stopped after the maximum iterations, I said. But I could also see quite fast that it was not getting significantly better. So it's not reaching this limit. So, yeah.
What I was thinking of, I mean, you try then to get the curves as close as possible with some engineering judgment, as I understand it. But it could be other things that are important. It could be the maximum deviation, or the time point when the maximum or minimum occurs, or the derivative of the frequency. That are the important things to look for.
Yes.
And then how the curve looks besides that is perhaps not so important, because that is when protections will trigger and other things, timing and maximum frequency deviation. So that might be something to check on.
Yes. This optimization only compares the measured with the extracted, or get to the minimum difference. And yeah, you can define, or I did define how it should be weighted.
Yeah.
So I had a higher weight on the first few seconds to get that good, and then I thought it was less important after a few seconds of this. Yeah. So prioritize the first initial response of the governors and AVRs.
Yes. So I have a few final questions here, and that is about simulations. You explain on page 180 that you made these 3 different cases investigated. That is the detail model, approximation 1 and approximation 2. I mean, I didn't really understand why you needed approximations. Was it simulation time, or it couldn't be, or why did you go for that when you have the full grid in this case? I mean, it's not 25,000 buses as in the European grid or something like that. So.
No, it was, of course, it reduces the computational time actually quite significantly.
Okay,
yeah. But also out of curiosity, because, if we use an approximation, we can reduce the computational time quite significantly. And it makes things a bit easier also with all of these regulators in the main grid and such. Just to see whether or not we can simplify it without oversimplifying it. Yeah.
Okay, but it was simulation times that was one reason why.
Yeah.
So how long time does such a simulation take with a full grid?
It doesn't take a long time.
Okay.
It's actually very fast, but especially when we take if we run these longer simulation, because in my study I have run simulations over several hours and such, and these take quite a long time. And when we then approximate the main grid, that helps a lot. But during this 30-second simulations, it's not a problem to simulate the main grid, but it simplifies the process of it.
Okay.
Yeah, and we also one thing is that in my simulations I have defined all of the loads and all of the tap changers according to the measurement data, and there are even though there are not that many, there are a lot more loads and transformers and such to check if I have the main grid in the system or in the simulation. So it's also to make that manual or that approach of using operational data in the simulation. You can avoid a lot of time spending on checking whether or not each load is specified as it should and each cable connection or circuit breaker is on according to the measurements. So if you only see the input from the main grid, you only have 2 parameters to adjust, active and reactive power.
Yeah, you mentioned on page 184, that is in the summary, that there are many other simulations that could be conducted, and you mentioned a few there. That is when the Suðuroy is connected. Are these the main ones you're thinking of, that with including that from 2026?
What I mean by that is that when we have this cable, and in my simulations post-2026, I have assumed that the cable is available. But we also have the risk of not having the cable available. And that will be a whole different situation for the grid on Suðuroy. Because right now we see that the main grid is contributing a lot to the stability. So a severe stability in Suðuroy is not that significant in the simulations. But also need to address it, what if the cable is out of service? And in addition to that, there have to be conducted more scenarios on the main grid itself, because all of this with the validated model have been focusing on Suðuroy. And here, one of the scenarios that will lose wind power production of 4.5 or something like that megawatts. And 4.5 megawatts compared to 60 megawatts in the main grid is not that a severe disturbance. But we need to check the severe disturbances in the main grid as well.
Yeah, one small thing I kind of neglected here or forgot was that you had no, the tidal power was not simulated dynamically.
Oh.
Because you have no good models, or you...
No, it was because I decided that the systems, the power system stability study should be based on the roadmap. And the roadmap does not include tidal energy. Yeah. So that's why.
It could have been of interest.
Yes,
also
it would, yeah.
Okay.
But I don't have the models either. So.
Okay, so I have one final question, which would be that, I mean, you, as I said at the beginning, I think you have done an impressive piece of work here, but it's always so that you can do more. Say that you got 6 more months to work on this topic. Where should you spend these 6 months? Where do you want to improve your thesis?
The stability study.
Okay.
After study. I think I'm really happy with the thorough expansion planning study that I've conducted, but I think there's still a lot of aspects in this power system stability that need to be addressed.
Any particular things?
No, just different scenarios and testing different control strategies and how we can avoid. In this, I have, for example, when I ran into some instabilities just increase the battery system or the synchronous condenser. But there are so many options to utilize wind turbines, or maybe reduce loads, or electric vehicles, or yeah. But due to the limited time, I just said, if we increase the synchronous condenser, then we can solve it. But there are so many other ways, and I think it's important to dig further into that.
Okay, thank you very much. So I would be finished with my questions then.
Okay, thank you very much. We will now have the break. We will have a break of 20 minutes, and then we will gather here again. So thank you.
But you covered already a lot of topics. so much on the computer. So this is, I like to know print it out.
Yeah. No, no. I mean, I have received it. The book I have read it. Yeah. But still, it's easier to make notes. So I have an easier to work on that page. So that's can be that. Yeah, right. You see it. People have. Yeah. Different colors. Right.
Yeah, I will be also shorter. So. Yeah.
He was the guy.
Okay.
And he was I saw him. And if he had the blood pressure there, I mean, with a big region, and he started really to go on this guy. Kind of good question. You have understood the thesis.
Okay, welcome back. We'll now go ahead, and I have not got any questions in the break, so we'll just continue right ahead with the next examiner, and it is Thomas Ackermann, Dr. Thomas Ackermann. So please, the floor is yours.
Okay, thank you very much. First of all, of course, I'd like to follow Jörn's initial comment. I think it's a great contribution, a great piece of work. I also said it this morning. I think it's quite important that this type of work is performed together with the industry actually, and that you also spread the results and the knowledge and the lessons learned out of it to the rest of the world, because it's not very common to have this kind of PhD thesis, which of course results also in many discussions, I think. I will try to have some more discussion or comments in the next, I don't know, half an hour or so. I would like to start with the scenarios and the roadmap development, of course. You mentioned yourself that, of course, further discussion is needed. Because the roadmap, as I understand it, is becoming, and we have seen it in different countries, an important decision-making tool, but it's not the final solution, how the system will look like. Just to give you a little bit, and maybe also the audience, an idea, a similar roadmap was done 4 years ago. The roadmap in Germany included no hydrogen, but a lot of gas. So basically, from today's perspective, you have to directly dump this roadmap and have to develop a new one. I don't know what this means for the Faroe Islands, but of course, I directly got stuck looking at the scenarios that you have suggested or that you have looked into. And I know the scenario development is difficult, particularly when you try to listen to different stakeholders that all have different interests. So my first question is, what additional scenario you might have in your head, but you didn't went through it, and why not?
Yeah. I don't know if I had any additional scenarios that I did not go through with. Because in addition to these 4 that I presented, I also have some more of a local concern, but you can say that I decided to not elaborate on that in, for example, my IEEE paper, or because I also have to separate what is technically interesting and what is a small decision that someone has to make, because are all of these scenarios making a huge impact on the systems? Because if you ask everyone, they will probably have a lot of different solutions. For example, someone will probably suggest to include expansions of hydro. But when you experience the resistance towards hydro, spending a lot of time on that might not be that motivating. Whilst, for example, tidal energy, which is still in the development phase, has gained a lot of interest in the Faroe Islands. And there are a lot of people who are interested in it, especially because they can utilize different locations and obtain the base load. But I don't think there was any scenario which I initially thought of including, but didn't include. Yeah.
Could you think now about a scenario that you probably think would have been interesting? I can sit here for like a long hour to discuss different scenarios that I found interesting.
Yes, there are, of course, I have limited myself to electrification of heating and transport and the traditional increase. And I've used a scenario which uses carbon neutral fuel. But then we could have a scenario stating where is this carbon neutral fuel being produced. For example, by power drags, and maybe we could include a scenario using that. But that would make the load different, because right now it only considers the electrification of heating and transport. But also we will see an electrification of the industry as well. And that has not been included here. So that's something that could be included as well.
Yeah, that's something I would have expected, that you include more demand-side management and industry demand, and more maybe also electromobility. I think there's no better place than using electric cars than here, where you don't have to drive more than maximum probably 150, 200 kilometers. So I would theoretically expect that electromobility will significantly increase, and you can have smart charging, you can have even vehicle to grid. And I was expected that this, like for example, comparing vehicle to grid or smart charging against batteries, what are the advantages, disadvantages? Why haven't you not included this?
Yeah. From the way my approach was that I will define this demand. And in the electric vehicles, I have included, or the pattern is suggesting that there is demand-side control. But as for the expansion planning study, I decided to not look further into to include all these different technologies because we're looking at an hour resolution, and yeah, I think my original plan was to look further into this with regards to the power system stability, to test on how much the electric vehicles, for example, could contribute with stability. But it was, I think the approach was based on the fact that we have a scenario, or the demand is defined and it's like that, and we'll not change that, but we will look on the generation side. But of course, this is also an aspect that should be investigated. Yeah.
Okay. Another option I was thinking about was, of course, offshore wind power, or also like einum wind power, and we'll come to this one later, different operation modes of wind power. I mean, wind power will have a significant future here, and I was a little bit surprised that you didn't consider more strategies on wind power. You also use, if I understand it correctly, in the model, mainly the existing wind turbines, like the E82 from Ackermann, also as a load curve, but you haven't played around with different load curves, with different ideas about different sizes, also different costs, which might give you more flexibility by using different power curves, basically, from different wind turbines, or even developing your own power curve.
I've used the one for E82, and again, if I would have to run different scenarios with different power curves and different wind turbine models, it would increase the amount of scenarios quite significantly, at least if I want to test it for all the different scenarios and how much impact it does. As for offshore wind power, when I started this expansion planning study, and also I think when the article on this was published, offshore was not discussed there. But since then, the interest in offshore has increased because we're having difficult placing wind turbines on land. But for the economic optimization, offshore is more expensive. So I doubt that it would change the simulations, because the optimization takes the cheapest solution. And since we have high wind speeds on land, then we wouldn't benefit as much as in other locations. But since Balmoral takes the optimal result, it would exclude offshore automatically. And it's the same with if I took different storage. And you also saw that battery storage, if you consider it for energy storage, it is quite expensive. And the model decides to invest in pumped hydro instead. But still we need some in Føroya to balance because of the distance. But someone also asked me some time ago if I considered hydrogen storage and such. But again, if the costs are higher than for the storage technology that I've used, then they wouldn't change the optimization. Yeah.
Okay, with offshore wind power, I understand this.
Yeah.
But for example, another topic I would have looked at would be more distributed photovoltaic, like rooftop photovoltaic, to also get more acceptance in the public that they can invest with maybe local storage. So instead of having one large storage, having distributed storage. Why have you not considered this?
It is to keep it on transmission level.
Okay.
And not go to the details of each specific village and what would the resource potential be there. And
I think you can model it actually quite simple. You don't have to go to different villages. You can make the same assumptions, but just have it geographically more distributed. But that depends on how Balmoral is working and how you set it up in Balmoral.
Yeah, for each location you need to define a resource profile. And if you want to obtain results which suggest that PV should be installed distributed, then you need to have these distributed resource profiles. In mine, I've used one resource profile for each region. But I'm not defining exactly where these are located. Of course, I base the costs on the PV plant in Sumba, in Surin. And that's not a rooftop solution. So the costs are based on that. But in terms of the region, I'm not decided that the location should be exactly there, but it can be within the region, since the PV, different from wind, can be placed on rooftops, on waters as well, and on large fields. And yeah.
I completely understand why you have to limit the amount of scenarios, also because you had a huge topic covering all the different ideas that you basically try to address in here. But of course, for the public discussion, I think this one will play quite a big role in the public discussion by limiting it to a certain amount of scenarios. I think you already make a prejudgment what might be actually discussed. And it's of course surprising that you have tidal power included, which I think from the results makes a lot of sense. It's very interesting, but it's still, in my opinion, quite early technology with a high risk involved in there. So I think some of the other, like demand-side management, where there are also very simple solutions available, might be a very interesting solution. So that's just something I think for me to keep in mind. I can completely understand why you had to limit it. I have more question. The title is Supply Reliability. How have you considered in the roadmap reliability? So is in Balmoral, can you choose like that all the scenarios have the same reliability, like loss of load probability, you can adjust it somewhere, or how is it considered in the roadmap, the reliability of the system? So do you have 100% of the demand is always supplied at all times?
Yes. Yes.
Well, that's unrealistic. So typically in most of these simulation models, you can choose what is like, what percentage of loss of load probability do you actually have?
Yeah.
Because there may be certain situations where you just have to accept that for an hour you have a blackout. And I think that's quite typical for this software tools. I have not worked with Balmoral, but in a lot of other tools I've worked on, you can adjust this one. So here you set it to 0 loss of load.
Yeah, I don't think there's such a parameter in Balmoral. But of course you can pretend you have a lower profile and then run another scenario. But as far as I understand you, this is a decision in the optimization.
Yeah, that's something you can typically influence. And of course, it's relevant that it's set for all scenarios similar, because you would like to have the same reliability for all scenarios. But it would be interesting, because the title of the thesis is, of course, aiming at supply reliability in with 100% renewables, that you discuss at one point what kind of reliability you have considered in the study, in the Balmoral study. I have to admit, I've read the thesis in different parts. It's quite long, so maybe sometimes I can't remember what I've read a couple of days earlier. But as far as I remember, it was not really discussed what is the reliability in the scenarios.
No, that's true. I've included all except from hydro. In hydro, I've used the production area. For all the technologies, I've used resources based on 2017. But for hydro, we don't have that many measurements of precipitation. But we have measurements of the production and the water level in the reservoirs. And based on that, I've calculated the weekly inflow. But during this year, 2017, there are 2 hydropower plants who are out of service for some time due to maintenance or something. And so, as for hydro, this has been included, that they are not all available. But for the other scenarios, I've included all of, I used 100% availability. But that being said, when I defined the power curve for wind power, I based it on first the E82, and then it has been adjusted according to what it usually produces in the Faroe Islands. So I've compared measurements with the active power, wind speed measurements and the active power. And so this is not as optimistic as the data sheet power curve.
Okay. Also, I mean, it's a lot about the method that you have applied. And as I said before, like, I'm more used to using roadmaps in a lot of the studies that I'm involved in. But we typically have another cycle, so that basically when you have a couple of scenarios, the results, you basically try to learn from all the different scenarios and then develop 2 or 3 more optimal scenarios from the lessons learned. And like for me, it would be, because the share of wind power is quite high, I would really start to discuss about different designs of wind turbines. So are they, like, as I understand it, you sometimes have nicer weather than today, then the wind contribution is quite small, but there's still a wind speed of maybe 6-7 meters per second. So if you can optimize a wind turbine by putting shorter rotor blades on it, but maybe shutting off at 20 meters per second, that they produce more during low wind speed conditions, and you have at least placed some of the wind turbines in there, that would be, in my opinion, like another interesting scenario to include.
Yes.
Have you looked into it? Have you discussed this with Ackermann also?
No, not at all. But I agree that is interesting, especially when you have, now I have this main scenario, and then you could investigate further what impact the different types of wind turbines or models of wind turbines would have. And this is possible to do in Balmoral, of course, but the way you do it is by defining the power curve. Mm-hmm. You need a different power curve. And cost, of course. Yeah.
But it's like, just like in New Zealand, for example, they have asked wind turbine manufacturer to change the power curve to the needs of New Zealand. So that's, of course, if you buy only one turbine, that might be not possible, but if you buy more of them, they might be willing to discuss this one. But that was also a couple of years ago when there was not a big market for wind turbines. Of course, with all the costs, like the roadmaps are based on the cost assumption, so it's more like shooting on a moving target. So the sensitivity studies or scenarios that you have put up is actually quite important. But I was missing the tidal power in there.
The tidal power?
Yeah, in the sensitivity scenarios, as like you have defined quite a small margin in there, like changes of costs and prices. But I would expect, like, it's not existing, or it's a technology under development, so you can have huge price variations there, and I would have expected a sensitivity study looking at a larger price range there.
Yeah. The reason I have not done that is because all of the sensitivity scenarios are based on the main scenario, and tidal energy is not included in the main scenario.
Okay.
Yeah, that's it.
Okay. Besides, I think Göran has taken a lot of questions that I had in mind, but I still have somehow I got stuck at the formulation roadmap validation. I think you also had a slide here. I'm just not sure if the wording validation is really what you mean there. For me, validation is something you're doing like a simulation and you test it against measurements. Yeah. But here, as I understand it, you validate two different simulations, two different things, and then you say, well,
yes,
the error is quite small, so we see it's validated. I'm not sure if the wording validation, I was not really happy with it. But
no, I understand that. What I mean is to validate that it's good enough, or to ensure that it's good enough, set to the requirements. But of course, this does not include any measurements. So.
And have you thought about a better name? So I was actually thinking about it.
No, because I haven't thought about it.
Is this part of the typically Balmoral approach to use it? No.
Balmoral is typically used by itself. So all the rest is something that I've added. But validation, I don't know. Verification, is that a better word, or that's maybe the same thing?
Yeah.
But what I mean is just to ensure that the roadmap meets the criteria that we've set.
Okay.
Yeah. Criteria check. I don't know.
Yeah, maybe criteria check. Okay. I would like to come more to a difficult question on the second part. Jumping a little bit faster, but my first question is, why have you done it at all? Stability study. Of course, it's in the title, and I think it was when you started your PhD, someone formulated into your objective. But do you really think that works together with a roadmap?
I think the roadmap is needed to conduct the stability analysis. Originally, we talked about the roadmap including only a small part, and the focus should be on the stability part. But how can we define the stability study, and how we, which scenarios we're investigating, and where are the wind farms placed and such? Of course, the roadmap is not what will be conducted as its whole, but it is a better foundation, I think, to conduct the stability analysis instead of just guessing and placing wind turbines and solar panels everywhere. Yeah.
The reason why I'm asking this one is I would normally say you get any system stable. I think some people will kill me for this one, but of course it's only a question of money, how much money you put into a battery or synchronous condenser. And you probably would do this kind of frequency study when you have the models of what you build from now on until 2028. And then I have a reasonably good power system model with at least the new equipment is very well represented. Maybe you have to do some of the parametrization, and then I would do the study 2028, and then in 2030 you had a battery system, then I can define how large the battery is. But I would would always say you get the system stable. For me, it's more like the question is, what do you have to consider with the equipment that will come from now on until 2028 or 2029? And for me, like a typical question would be, do we need grid forming? How much grid forming do we need? Do we have to work on the grid code to consider different aspects? That's something that I was considering part of a stability study. So for me, it was a question as, how much have you considered this one, or how much have you thought about, for example, the grid forming capabilities that you need until 2030 in the equipment that you will install from now on? Should this be part of the grid code? Should all new equipment that comes on from next week on could have grid forming? Or do you need only 20% share of grid forming or 30%? Have you investigated or have you looked into this one?
No, I have not. I have not considered grid forming. And it was also because of, yeah, as I said, when I started, the roadmap should be a really small part, but it became half of the thesis. And then I had to validate and parameterize the model. So when I got to this actual stability study, there was not that much time left, and therefore I decided to assess the ancillary service by just increasing battery systems and synchronous condensers instead of investigating all the different options and to be able to see what impact grid farming, for example, could have on the system.
Okay.
Yeah.
I think with, of course, the model development and the parametrization, I think you have done, I know that's really difficult, and I know that's also challenging to do, and I know that's demanding. Of course, you said before when Göran asked that you have not found any guidelines, for example, what is the acceptable error margin. Of course, different people have the same problem, and you can find some studies or comments, articles about this one. Also in the German grid code for the validation of equipment, it's actually defined what the variation between grid models that you actually develop and simulation tests should be. But of course, these are lab tests. These are based on step load tests in the lab, and there's a maximum variation is, I think, 10%. We had projects where actually our client said you should have not more than 5%, which is absolutely not doable. I think you should have at least have some discussion about what Göran also said or asked about the range and in which area you should, what is acceptable in terms of your parameterization. Maybe also a side comment. I was surprised, I can understand, of course, that for the really old hydropower stations that you can't get the grid models. But for many other things, I would have assumed that manufacturers are still giving the old data or the data of the equipment that they have installed. And there's a small tip, that's my experience, if you say you want to buy more, if they basically tell you the old grid data, they suddenly go down in the archives and find the data. Yeah. That's just a small tip, but that can save you a lot of work in the future. Yeah. What else? That's maybe something I need some guidance from you, from the stability study. When you go out now, you see that all the wind turbines are currently built at the same location. Have you considered this one already, that there's something happening in your system which you cannot reverse? And have you considered this in the stability study, that basically you get a lot of wind power in the same location?
No, I have not, because as I mentioned previously, the stability study was conducted based on the expansions in the roadmap, and all of this with the close wind farms placed close together happened afterwards. And then we had a discussion on should they change the expansion plan, and I don't know, especially since I was limited to investigate the stability in Føroyum. It was not that crucial to include these new developments in the main grid, because I'm focusing on Føroyum, and these wind farms that are placed close together are all in the main grid. But of course, and I already started that, to include all of these models on that are placed close together, and that is something definitely that has to be investigated.
Yes, I think that's really like the challenge with this kind of, actually the challenge for the utility and everyone involved in planning, that you shoot on a moving target. So for me then the question is, how easy is it for you to replicate everything? Have you, like also maybe a second person, someone else, to replicate some of the studies with a new setup, which I would consider extremely important?
To replicate the stability studies?
Yeah, with like the changed...
It is relatively easy, I would say.
So if you have the 6 months, extra 6 months that you mentioned, you can do it basically.
Yes.
Okay. I also had one topic, how you approach the loads. That was a big question mark from my side, because I think there's a lot of documentation how to model loads and dynamic loads, and also many things that Göran said. I think that's something you should probably include in the future modeling, particularly the compressor loads and frequency-depending loads. Mm-hmm. I originally wanted to discuss more about grid forming and also about, for example, using wind turbines for frequency control. How much have you included this one? Also like running wind turbines in delta control, that they really can ramp up and down, not only the frequency, basic frequency control, but also really have a balancing capacity, but that of course reduces the economics. But basically you can replace some of the batteries using wind turbines running in delta mode.
The only thing that I've tested with that regard is the inertia emulation capabilities of the wind turbines. I've not played around with different control strategies, as we decided to use the settings that are used now, and the settings that are used today are set point regulation. Yeah, that's the limitation as well. But I decided to use to test the inertia emulation because that was the easiest control approaches to test. Because if we were testing all these different control strategies that the wind turbines are equipped with, you also need to parameterize these controllers. Because right now, the only controllers that are parameterized are the ones that are in use. So this is just some additional work, while the inertia emulation is something you activate and deactivate, which is currently deactivated in the Føroyum. Yeah.
So I think there's certainly more space for more work.
Yes.
The last question, of course, for the stability study and the frequency, you mentioned before the typical frequency range here is 49.5 to 50.5. This is like the planned frequency that you would like to operate at. I would expect also going to 100% renewable that you might have to discuss if this is the economic optimum. I think there's no reason why you not should basically allow a little more frequency variation, at least at certain times. That's of course discussed in some countries. But I think that's another topic for discussion and including in there. Otherwise, I would really like to thank you. I think I really enjoyed reading your thesis, even though it's quite long. As I said, I'm really looking forward to the additional work that you might do. I think there's more work needed in this area, and I think the Føroya is a really interesting area to investigate some of these issues, which most likely will be relevant for a lot of countries in the next coming 10, 20 years. So thank you very much.
Thank you.
Okay, thank you very much. Now the examiners will go to another room to assess the overall work of Helma Maria. We don't know how long they need to be there, so don't go too far. You may be able to stretch your legs a bit, so just be around. Okay, thank you.
Godt temperatur på kurven. Ikke rimelig. Ikke? Kom igjen.
kan lukka nevna her at det Tjóðheim som vilja og hava interesse for hisnir arbeid og meira djupgengande. Her det som muligt at få et eintak av rikjørene. Og det rikjør her i Esjon her ivre. Så hvis det onker som vil fordjupa seg meira og i tog som Helma Mariu har gjort, så det mulig å få oss her og gjøre det.
Right, Helma Maria. We have authored a report of 4 pages regarding the thesis and the oral examination. And I will only read the last part of the conclusion, and you will be handed the document afterwards, so you can read the entire document. So, in conclusion, the context and relevance of the research topic has been thoroughly established with a solid review of scientific literature, available data, and practical experience from around the world. A 100 by 2030 roadmap has been presented and critically discussed. Simulation models have been developed, parametrized, and validated with a full-scale system. This is rare for a PhD project. The presentation during the defense was clear and structured. Questions posed by the examiners were answered in a calm and comprehensive way. Based on the thesis and the oral examination, we conclude that you, Helma Maria, Helma Maria is a very strong researcher and engineer, both theoretically and practically. The committee unanimously recommends that Helma Maria is awarded the PhD degree.
Mariu